Have you ever wondered how a brilliant discovery in a lab actually becomes a massive multi-million-dollar chemical plant? Well, it all comes down to the fundamentals of process engineering. It's the art and science of visualizing, quantifying, and really evaluating complex chemical systems on a huge scale. So let's break down how it all works.
Here's the game plan. We'll start with the basic architecture of any process, then jump into how we visualize it all with diagrams. From there, we'll get into the math, the core balance equation that governs everything. After that, we'll look at the key metrics for success, and we'll wrap it all up with a real-world distillation case study. Let's dive in.
So, you're faced with designing a sprawling chemical plant. Where do you even begin? Well, the secret is to realize that any complex process can be broken down into fundamental, totally manageable building blocks.
And that building block has a name, the unit operation. This idea, first put forward by Arthur DeHaan Little way back in 1916, was absolutely revolutionary. It basically said that any industrial process, whether you're making pharmaceuticals or refining petroleum, is really just a unique sequence of the same fundamental steps, all governed by the same universal laws of physics.
And these unit operations, they fall into just a few key categories. You've got mass transfer operations, which are all about separating components, think distillation. You have heat transfer for managing energy with equipment like condensers. Fluid flow is pretty self-explanatory. It's about getting stuff from A to B. Mechanical operations handle solids, and thermodynamic operations leverage principles like refrigeration. Seriously, every plant you can imagine is just a different combination of these core ideas.
Okay, so if a plant is just a collection of these building blocks, how do we actually represent them on paper? Let's move on and see how engineers use a very specific visual language to map out an entire process from start to finish.
Everything starts with the block flow diagram, or BFD. You can think of this as the 30,000-foot view. Each major step is just a simple box connected by arrows. It's perfect for getting the core concept across to, say, management without getting bogged down in all the nitty-gritty technical details. For instance, if we were making orange juice concentrate, the BFD would just show the main path. Fresh oranges come in, they get washed, juice is extracted, water's evaporated out, and then it's packaged. It clearly shows the main product flow and points out where things like solid waste and water vapor leave the system. It's all about the big picture, simple, clean, and effective.
This is great for an overview, for sure, but it's missing all the numbers, right? All the specifics we need to actually design something. So how do we add that critical layer of engineering detail?
We level up, we move to the process flow diagram, or PFD. Now, this is the true engineering blueprint. Those simple blocks are replaced with standardized symbols for real pieces of equipment, and crucially, it's paired with something called a stream table that contains all the numbers, flow rates, temperatures, pressures, you name it.
This table sums it up perfectly. You see the hierarchy here. The BFD is for the conceptual overview, for management. The PFD has all the process data for the engineers doing the design. And then there's the PNID, which has the absolute highest level of detail. Every single valve, every instrument, for the operators and technicians who have to run and maintain the plant. Each diagram serves a very specific purpose for a very specific audience.
All right, so we have our visual blueprint. But to make it truly useful, we need the math to back it up and quantify what's flowing through those pipes. This brings us to the single most important law that underpins all of process engineering, the conservation of mass.
This is it, the general balance equation. It's basically a universal accounting tool. You can apply it to anything, total mass, moles of a single chemical, even energy. All it says is that the change inside a system, its accumulation, is simply what comes in minus what goes out, plus anything that's created inside minus anything that's used up inside.
The way you use this is you first have to define your system by drawing a boundary around it. Input and output are things that cross that boundary. Generation and consumption, well, those happen inside the boundary. Think chemical reactions. And accumulation is just the net change over time within that boundary you drew.
Now, that full equation can get pretty complicated to solve, but for most large-scale continuous industrial processes, we can make two incredibly powerful game-changing assumptions. First, we assume steady-state operation. That just means nothing is changing over time, so the accumulation term is zero. Poof, it's gone. Second, for purely physical separations like evaporation, no new chemicals are being created or destroyed, so the generation and consumption terms are also zero. And what happens when you do that? That entire complex equation collapses into this beautifully simple, elegant powerhouse of a statement. Input equals output. What goes in must come out. This is the absolute cornerstone of continuous process design.
So let's use it right now on our orange juice evaporator. Say we have 10,000 kilograms per hour of juice coming in. Using input equals output, we can write two simple balances. First, an overall balance. The total feed in has to equal the water vapor out plus the concentrate out. Then we do a solids balance. All the solids that come in with the juice have to leave at the concentrate because no solids are in the water vapor. With those two simple equations, we can solve for our exact product and waste stream flow rates. It's that powerful.
Okay, so now we've calculated all the flows. But how do we know if our process is any good? How well is our separation actually working? That brings us to our performance scorecard. We need some key metrics to evaluate the process.
The first key metric is purity. This one's pretty straightforward. It's just the concentration of your desired product in your final output stream. It is a direct measure of quality. For something like pharmaceuticals, 99.9% purity isn't just a goal. It's a matter of patient safety and getting regulatory approval. Purity is what drives the market value of your product.
The other side of that coin is recovery. This metric is all about efficiency. It asks a simple question. Of all the valuable stuff you put into the process in the first place, what percentage did you actually manage to capture in your final product? High recovery is absolutely critical for making money. You can't afford to just dump your expensive raw materials into a waste stream. Now, specifically for a separation process like distillation, there is one number that is king. It's called relative volatility, or alpha. This is a fundamental thermodynamic property that tells you how easy or how difficult it will be to separate two chemicals. It's basically a ratio of their tendency to vaporize. A high alpha means one chemical is way more eager to turn into a gas than the other, which makes separating them a breeze. And the value of alpha tells you everything you need to know. If alpha is greater than 1, congratulations, separation is possible. The bigger that number, the easier and cheaper it will be. But if alpha is exactly equal to 1, you have what's called an azeotrope. The components have identical volatility, and that means separating them by conventional distillation is physically impossible. You're forced to use a much more complex and expensive technique.
Okay, it is time to put this all together. For this final section, we are going to integrate everything we've talked about. The diagrams, the balance equations, the metrics, and perform a complete analysis of a distillation column from start to finish.
So here's our task. We need to separate a feed of 100 kmols per hour of a benzene and toluene mixture. Our goal is to get a distillate product that is 98% pure benzene and a bottoms product that is 96% pure toluene. And here's the key piece of data. The relative volatility, alpha, is 2.4. Since that is significantly bigger than 1, we already know this is a very feasible separation.
We just apply our powerhouse input equals output principle. We can set up two balance equations. First, an overall molar balance. The 100 kmols per hour we feed in has to equal the distillate flow D plus the bottoms flow B. Then we do a component balance just on the benzene. Now we have two equations and two unknowns. We can solve those simultaneously and find that our distillate flow rate is 38.3 kmols per hour and our bottoms is 61.7.
So our purity specification was 98% benzene, and we designed for that. But what about our recovery? Well, when you run the numbers, you find we're capturing 93.8% of the benzene that we originally fed into the column. And this right here perfectly illustrates that classic trade-off in process design. To achieve that incredibly high purity, you almost always have to accept losing a little bit of your valuable product out the other end.
And here it is. This is the final deliverable. All of our work, from the problem statement to our calculations, gets summarized cleanly and professionally in a stream table like this one. This is exactly what would accompany the process flow diagram, giving any engineer all the essential data for the feed, distillate, and bottom streams in one clear format. So let's end with this thought. We've gone all the way from simple blocks on a page to detailed calculations, but it all hinges on these fundamental principles. And it leads to a really fascinating question. How can just one number, that abstract thermodynamic property, relative volatility, end up dictating the entire design, the cost, and even the ultimate feasibility of a multi-million-dollar chemical plant? That right there is the power of process analysis.